Hello, my name is Nan Wang. I am a postdoc research fellow in CSIRO, the Australia's National Science Agency. In this video, I'm going to present our work, SwiftRange, a short and efficient zero-knowledge range argument for confidential transactions and more. This work is completed by me, Sid, and Dongxi. Part of work was conducted when me and Sid were within Australian National University. First of all, let me give an outline of our contributions. In this paper, we developed a new type of logarithmic sized zero-knowledge range proof in the discrete logarithm setting, called SwiftRange, without using a trusted setup. It can prove a committed value lies in the range between 0 and 2 power n minus 1. Our proof is designed to be a competitor to another state-of-the-art range proof called bulletproofs. Compared to it, for 64-bit range, our proof achieves twice verifier efficiency, 1.4 times prover efficiency, at the expense of 1.1 times communication costs. It can be a drop-in replacement for blockchain-based confidential transactions and more other applications. Let me give a brief introduction to the background. Blockchain leverages cryptographic techniques to link blocks together. Blockchain enables decentralized peer-to-peer transactions without using a central authority. The technology has spawned the creation of various cryptocurrencies, such as Bitcoins and Ethers. Each block consists of a multitude of transactions, where each transaction contains three key data: a sender's address, a recipient's address, and the transfer amount. However, blockchain does not provide transfer amount privacy and has poor scalability. Scalability refers to the processing capacity of transactions within a specified time frame. Privacy and scalability used to be the two major bottlenecks of blockchain systems. After 2013, the emergence of confidential transactions addresses the privacy issue. Let us see what are confidential transactions. In normal transactions like Bitcoins, the transaction amount is publicly visible. In confidential transactions, the transfer amount is hidden from outsiders. Only the transacting parties know the transfer values. Some confidential transaction schemes even hide the sender and the recipient by using other cryptographic techniques. Hiding transaction amount raises a technical challenge for confidential transactions, which is, how can we ensure the hidden amount is non-negative? If a sender transfers negative values, then there will be serious problems. Malicious parties will be able to create new values out of thin air. This is where zero-knowledge proof, range proof, come into play. We employ public coin protocols to construct our range proof. Let me give a simple example on how to construct a public coin zero-knowledge proof. A public coin zero-knowledge proof is an interactive protocol between the prover and the verifier, where all the verifier's messages are uniformly random and independent of the prover's messages. It can prove the knowledge of a secret without revealing it. A prover sends an initial commitment in the first round, then the verifier replies with a random challenge. In the third round, the prover must send back some values computed with this challenge. And finally, the verifier can use these values to conduct verification. The popular Fiat-Shamir transformation can help transform the interactive protocol to a non-interactive one. Let me provide the technical details. Our full protocol is composed of a new range protocol and a series of compression protocols. Our range proof has a linear proof size. The compression protocols aim to recursively reduce the linear proof size to logarithmic size. We propose a verifier-efficient variant of the bit decomposition approach to prove that a committed value X can be represented in a binary form. Let me provide the technical details of our range protocol. Given a commitment big X and the committed value small x written as a weighted sum of a binary vector B, we design a new equality without considering zero knowledge, which only involves n+1 distinct generators, only half the number used by bulletproofs. There are two parts separated by a random challenge E on the left-hand side of the equality. For the left part in blue frame, we rewrite G to the power of the weighted sum to the product of a series weighted generators, where the ith generator is G to the ith powers of 2. The right part in blue frame is a series binary constraints imposed on the bit vector B. By achieving zero knowledge property, we substitute the bit vector B with the masking vector Z into the core equality. We obtain a verification equation on the right side of the slide. We can see that after substitution, we have a constant term enclosed in blue frame on the right-hand side of the equality. If this term is cancelled out, the verifier can be convinced that the masking vector hides the bit vector that constitute the committed value X. The hardness of discrete logarithm relations between any two generators imply that each element in the bit vector is either 0 or 1. Furthermore, we made a transformation to obtain a composite generator H by merging the generators whose exponent values are Z. This facilitates the following compression. Then we introduced the compression protocols. Atma et al. Presented a compressed sigma protocol for linear setting in their paper published by Crypto 2021. We created an adapted version by adapting it for quadratic setting. Our adapted protocol can effectively compress our range protocol to achieve logarithmic communication complexity. First, we begin with a brief introduction to the original compression protocol for linear setting. Given a witness vector Z and a generator vector G, satisfying the relation G to the power of Z is equal to a group element W. The trick is highlighted in green color, where the prover recursively reduces the dimension of the generator vector G and the witness vector Z until the dimension is equal to 2. Note that to compute the generator vector G prime, the prover raises the left subgenerator vector to the challenge C. In this case, when computing W prime, there's an exponent C on the value W. So in the next recursion, the element A, W, and B of the current recursion must be raised to the power of the challenge C prime of the next recursion. In this case, all the previous recursions must always consider the subsequent recursions. This increases additional computational overheads. We adapted for a quadratic setting. Given a witness vector Z and two generator vectors H and G, satisfying the relation H to the power of Z times G to the power of minus Z squared is equal to a group element W. We made several modifications highlighted in red. The prover recursively reduces the dimension of the generator vector and the witness vector z until the dimension is equal to 8. Note that we applied a trick when computing the generators h' and g'. We raised the right subgenerator vector to the power of c power minus 1 and c power minus 2, rather than raise the left subgenerator vector to the power of c in the original compression protocol. The trick ensures that in each recursion, W does not have exponents. This optimization effectively decouples the recursions to save computational overheads such that the group elements of previous recursions no longer need to consider the challenges of subsequent recursions for verification. We have to terminate the recursion earlier because each recursion involves 4 group elements instead of 2 in the original protocol due to the quadratic setting. Finally, let me show you our experimental results. We conducted a comprehensive benchmarks of the performance of our proof against 2 state-of-the-art range proofs in the discrete logarithm setting, namely flash proofs and bullet proofs. And by the way, I'm also the first author of flash proofs, which is published in AsiaCrypt 2022. Regarding single proofs, both our proof and bullet proof have logarithmic communication complexity. Our proof runs faster than bullet proofs at a slight expense of communication costs. Flash proof had the fastest prover and verifier, but the proof size is not logarithmically small. At the time of writing, our proof for 8-bit ranges also achieved the smallest 353 bytes proof size among all the bit decomposition-based range proofs without using a trusted setup. Our range proof also support the aggregation of multiple single proofs created by one prover. Let us see the efficiency comparison of the aggregate proofs. Similar to single proofs, our aggregate proof also gains a notable advantage in prover and verifier efficiency with relatively small communication costs compared to bullet proofs. Our aggregate proof presents a logarithmically quicker growth with an increased aggregation size than bulletproof-based ones. Flash proof is still the fastest with increased aggregation size, but its proof size is far larger than those of our proof and bullet proofs. In conclusion, our proof and bullet proof are well suited for applications where the communication efficiency is critical, while flash proof is more suitable for the computation critical scenarios. Our range argument can be applied to various practical applications for preserving privacy, not limited to confidential transactions on blockchain systems. We enumerate some example applications such as black box accumulation schemes, privacy-preserving cross-sensing, collaborative consumption, and smart IoT, etc. In these scenarios, users provide committed values and can be required to provide a zero-knowledge range proof to prove that their provided values are within the allowed ranges. This can prevent any malicious users from sabotaging the execution of these applications. Thanks for watching. Please refer to our paper for the full details.